All right, so we're starting with 3.5 rational functions and their graphs. The main thing we're going to focus on in this section, though, once again, we're not doing too much detail with graphs. We've already been there, done that. I know that you guys are pros at graphing at this point. The main thing we want to focus on, though, which is something new in comparison to what we talked about as far as graphs are concerned, are your asymptotes. These are going to be places where the function is undefined or does not exist, or places where the graph does not cross or will not cross. So there are three types of asymptotes. All right, so we have vertical asymptotes. So we have three types of asymptotes. We have our vertical asymptotes, horizontal asymptotes, and our slant, or sometimes called oblique asymptotes. All right, so we're going to talk about how to find all three. Once again, that's all we're going to focus on in this section. Let's see what we'll explain. Let's do that. All right, so your vertical asymptotes is going to be where your denominator is equal to 0. First thing we'll do is simplify as much as possible. That's always key because certain things will be able to cancel out for us, which will dictate whether we have what our vertical asymptote or vertical asymptotes will be. So you want to simplify as much as possible. I said as possible. I meant as much as possible. So how about I do this? As much as possible. All right. So simplify as much as possible and then set the denominator equal to 0 and solve. All right, so the first example, I want to find the vertical asymptotes, if any. All right, so we have x over x squared minus 9. That's the first one. And we want to set that x squared minus 9 equal to 0. If we want, we can factor it. Or you could add 9 to both sides. Up to you. Either way, you still get the same result. All right, so we have two vertical asymptotes. I guess I'll go purple here. One is at x equal to -3, and one is at x equal to 3. And that is important that you hold true that to the statement that x equal to -3, x equal to 3. So what'll happen is when you go to graph it, you have vertical asymptotes, at 3 and at -3. They have these imaginary lines that your graph will not cross. So your graph could look something like this. I haven't looked at the graph, but it could look something like that. It's just that you have these imaginary lines at 3 and -3 that your graph will not cross. As far as vertically, anyway. We'll talk about horizontal asymptotes in a second. All right, questions before we look at B? All right, so here we have x plus 3 over x squared minus 9. So remember I said simplify as much as possible first. So if I were to factor that denominator, we see that the quantity of x plus 3 will cancel, leaving me with 1 over x minus 3. All right. So this right here, this x minus 3 will produce a vertical asymptote. But this x plus 3, we still have to give an account for, and I'll do that before we close out this example. But I just want to make sure we understand this right here. Well, let me do this. This right here will produce vertical asymptote, and then this one will produce a restricted value. So you still have to give an account for it. It's just not an asymptote. It's just a value that you can't plug into the equation because you still get 0 in your denominator when we look at our original function. All right. So if I go ahead and set both pieces equal to 0, and just remember which one is going to give me what. Matter of fact, I'll stay green. So the restricted value is going to be x plus 3 equal to 0, which would be x equal to -1. And the vertical asymptote, x minus 3 equal to 0, is x equal to 3. So that's how you would do that. Because they may ask you, what's the vertical asymptote, and are there any list any restricted values. So you would give x equal to 3 as a vertical asymptote, and -3 would be a restricted value. All right, questions on that? All right, one more out of this example before we look at horizontals. X plus 3 over x squared plus 9. So when we look at x squared plus 9, cannot factor that. So we don't have to worry about trying to cancel that out with x plus 3. Remember, you can factor x squared minus 9. You cannot factor x squared plus 9. So that's the difference between the difference of squares versus the sum of squares. So we cannot factor that. And then if I were to set it equal to 0, since I can't factor it, I have to solve. I will subtract 9 from both sides. Then take the square root of both sides. And I have x is equal to plus or minus 3i This is imaginary, and there's no such thing as an imaginary asymptote. As far as the value is concerned, the line is imaginary by itself, but so this means no vertical asymptotes. If you can't solve it and get a real number, then there are no vertical asymptotes. And then if you think about, remember we've done find the domain before, it's the same thought process. When you're trying to find the domain of x, what you can plug in versus what you cannot plug in, x squared plus 9 does not produce any values that will create 0 in my denominator. All right. It's impossible. So someone asks us why we can't factor it. Now you can factor using imaginary numbers, but normally when you're talking about factoring, you don't want to use imaginary numbers. There's no combination as far as a breakdown is concerned that will give you x plus 9. So when you look at x squared minus 9, that's x plus 3 times x minus 3. If I were to multiply these back out, it would give me this. But when I look at x squared plus 9, there's nothing I can multiply. If I do x plus 3 times x plus 3, I would end up getting x squared plus 6x plus 9. If I were to do x minus 3 times x minus 3, I get x squared minus 6x plus 9. So no, there's no combination without using imaginary numbers that you can use that will break down from this x squared plus 9. Okay, cool. All right. So any questions on those three before we look at your horizontal asymptotes? All right, so horizontal asymptotes, as a matter of fact, nah, I won't do that. Okay. All right, so your horizontal asymptotes, all right, so we're gonna let n be the degree of the numerator and m be the degree of the denominator. So what we're talking about when we say degree, we're talking about the highest exponent of the polynomial in the numerator or the highest exponent of the polynomial or expression in the denominator. So, and the only reason I'm using this terminology versus writing it out without saying those things is this is how the terminology is expressed in the book and probably in my math lab. So the degree of the numerator is the highest exponent, in the numerator, and then the degree of the denominator, highest exponent in the denominator. So that's what we're talking about, degree. So quick example before I go into the actual thing. I'm gonna erase this, but I'm just showing you what I mean. If my function says x squared plus 5x minus 3 over, I don't know, 8x plus 7x plus x to the fourth, the degree of the numerator is 2 because that's the highest exponent. The degree of the denominator is 4. That's the highest exponent down there. All right, so that's what I'm talking about when I say degree of the numerator versus the degree of the denominator. So like I said, I'm going to erase this because we're going to have our examples, but I'm just throwing it out there to make sure we have clear understanding before we keep moving. So we have 3 scenarios. N is, let's do less than. I should make more room. That's done now. I put a 4. Why did I put a 4? All right, so here are our 3 scenarios. For scenario 1, if your leading coefficient is less than, not your leading coefficient, your the degree of your numerator, the exponent, the highest exponent in your numerator is less than the highest exponent in your denominator, then your horizontal asymptote is y equal to 0. Once again, notice here now we're using y. Remember before when we were looking at the vertical asymptotes, we were looking at x. Now we're looking at y. So y is equal to 0. If the highest exponent in your numerator is less than the highest exponent in your denominator, y is equal to 0. If your exponents are equal, then we're going to take the leading coefficient of your numerator and place it over the leading coefficient of your denominator. Once again, y equals. Then for the last scenario, if n is greater than m, in other words, the highest exponent in your numerator is greater than the highest exponent in your denominator, there is no horizontal asymptote. We will actually go to the slant asymptotes. That will be what will send us to the slant asymptotes. All right. Questions before we try it? All right, so let's try this out. So find horizontal asymptote if there is one. All right, first one, we have f of x is equal to 4x over 2x squared plus 1. When you don't see an exponent, remember we're looking at our exponents, that's going to dictate which scenario we're in. If you don't see an exponent, remember they assume there's a 1 there. So n is equal to 1, m is equal to 2. So n is less than m. So that means my horizontal asymptote is equal to 0. So remember that was our first scenario. If n is less than m, my numerator exponent is less than my denominator exponent, and y is equal to 0. All right, so we have 4x squared over 2x squared plus 1. Next one, looking at our exponents, n is equal to 2, m is equal to 2. Since they are equal, that means y is equal to the coefficients of each one. Numerator over denominator, 4 over 2. So that means y is equal to 2. Of course, it's not going to always be a solid integer for you. If it stayed in fractional form, then of course you would just leave it in fractional form. So if it reduced down to 2/3, it would just be 2/3. So you don't always have to look for a solid integer. Questions before we look at C? So for the last one, my numerator is exponent, or the degree of my numerator is 3, degree of my denominator is 2. So that one, my numerator is greater than my denominator. That means that there is no horizontal asymptote. So for this one, since there is no horizontal asymptote, that will send me to the mindset of now trying to find my slant asymptote. The way that the problems are set up for you guys, now you can get into more complex problems, more problems with things added to it to make it more involved. But for the problems that you guys have, if you have a horizontal asymptote, then you will not have a slant asymptote. You have either or. Okay. So once again, we go through our 3 scenarios. The first 2 let you know where you will have a horizontal asymptote. This third scenario lets you know when you will not have a horizontal asymptote. And actually it lets you know that now you can go looking for a slant asymptote. Okay, so before we go into our last asymptote for the day and close out this section, questions. All right, so how I want to write this. I say horizontal asymptote, slant asymptote. Do one do long division. I'll just say, well, I can say or use long division or
Is this my birthday thing or?
got a question for me? I guess not.
Not really, right?
Okay, so let's go through it. Basically, we have to go back and lean on our division of polynomials techniques. So whenever n is greater than m, remember that was that third scenario, then there should be a slant asymptote. So we'll use long division or synthetic division if possible. We talked about synthetic division to find. And so whenever you divide out, your answer takes on the form of your quotient plus your remainder, over the divisor. So y equal to the quotient, that is going to be a slant asymptote. So we won't need the remainder, but that first part will be a slant asymptote. So let's look at a good one. So here, find the slant asymptote. We have x squared minus 4x minus 5 over x minus 3. We can use not slant, we can use synthetic division on this one just because of the way that it's set up. Or we can use long division, doesn't matter. I'll just go ahead and use synthetic. Because remember, if you have one is your exponent in your denominator, one is your coefficient in your denominator, then you can use synthetic division. So you use the opposite of this -3, which would be +3. Write down your coefficients. That'll be 1, -4, and -5. We bring down 1. 3 times 1 is 3. Take it over here and then add these together and keep that same pattern. So -4 plus 3 is -1. 3 times -1 is -3. -5 plus -3 is -8. So if I were to write this out, you always start with 1 less than the degree we originally had. So it's going to be x minus 1 plus -8 over x minus 3. So this part right here is your slant asymptote. So y equal to x minus 1. It's my slant asymptote. All right. Questions. Guess we can do at least one more. What was this one? X squared. I think all of them are just doing. Nope. Okay. All right, so let's do this one, and then we'll actually be done for this section anyway. X squared plus 1 over x minus 1, looking for that slant asymptote. Once again, I can go ahead and use synthetic division because of the setup my divisor. So I'll throw +1. I want to do blue. +1 into the box. Now here, don't forget you have a missing term. And that missing term is x. We went from x squared to no x at all. So you have to give an account for that when you write down your coefficients. So you have 1, 0, and 1. And so this is that missing x term right here. You have to give an account for that with a placeholder. All right, bring your 1 down. 1 times 1 is 1. Add them together, that's 1. 1 times 1 is 1. Add them together, that's 2. Once again, we'll start off with 1 less than the original exponent that we have. So that's going to be x plus 1 plus 2 over x minus 1. That's the whole answer. But remember, this is the part that is our slant asymptote. So our slant asymptote is y equals x plus 1. So don't forget your vertical asymptote is x equals your horizontal asymptote, and your slant asymptote will be y equals. All right. questions, questions, questions. Okay, so in chapter 3, we still have 3.6 and 3.7 to discuss before we actually complete the chapter. So we're still okay as far as that's concerned. Feel free to shoot me emails if you have any questions. And then also you can ask them just like, people ask questions today. I will do my best to, address them in class as well. So outside of that, you guys have a great one. Be safe, and I will see you on next class. All right, everyone take care.
Thank you.